In this video, we're going to discuss Bayes' theorem. This is an interesting outcome of the discussion that we had previously on conditional probabilities. With conditional probabilities, we're usually interested in the effect of a prior event on events that follow it, as far as their probability is concerned. Bayes' theorem is the other way round. We're going to explore the non-intuitive result that the outcome of an event, a subsequent event, changes the likelihood of an unknown prior event. Usually for conditional probabilities, okay, we have an example like this, okay? For example, if you, what is the probability that you test positive given that you have cancer? Let's say we have a blood test for a certain type of cancer. This is called the test sensitivity, and it's something that's usually known. You can think about it from the point of view of a medical professional, okay? You would want to know how sensitive the test is. Can it pick up cancer if a person has it? Okay? Here's the Bayes probability in the second example. What is the probability that you have cancer given that you test positive? Excuse me. This is really what you need to know about your test results, if you think about it. Let's consider a quality control situation. Suppose we know that 75% of the transistors a given corporation, Acme manufacturers, are produced in plant A, and the rest of them, 25%, are produced in plant B. Based on historical information, we know that 90% of the transistors produced in plant A are good, and 10% are defective. As far as plant B is concerned, we know 95% of what plant B produces are good, and 5% are defective. We can build a probability tree showing this information. Again, 3/4 of the transistors are produced in plant A, and the remaining quarter are produced in plant B. Here are the conditional probabilities for good and defective. If a transistor, okay, is produced in plant A, there's a 90% chance it's good. If it's produced in plant A, there's a 10% chance it's defective. So if we're looking at a given transistor in a quality control sample, the probability that it's from A and good is the product of the branch probabilities that get you to A and good. Okay, so 90 times 75%, or 0.675. Likewise, the probability that the transistor is from A and defective is the product of those branch probabilities, or 75% times 10%, 0.075. If we're interested in knowing the probability that a transistor is produced in plant B and good, we follow that branch and multiply the probabilities to get 0.2375. And likewise, the only other alternative is the transistor is manufactured in plant B and defective, and the product of those branch probabilities, 0.25 times 0.05, is 0.0125. Again, if you add up all of these branch probabilities, you should get 1. Let's take a look. Okay. If you want to know, again, the probability of finding a good transistor, you've got to consider all the ways to get a good transistor. Okay, that's either following this branch through plant A to good, okay, which gives us 0.675, or following this branch through plant B to good, which gives us 0.2375. So if we want the probability that we have a good transistor in our hand, we're just going to add together those two branch probabilities. So we have a 91.25% chance our transistor is good. Likewise, the other two branches will give us the probability that we have a bad transistor. We're going to add those, and we get a 0.0875% chance. Again, you can see these two numbers, 0.9125 and 0.0875, would add up to 1 because the transistor is either good or it's defective. There's no other choice. Here's a table view of what we know. Okay, again, this is plant A and good. Okay, so that's the result of the first branch. Here's plant A and defective, that's the second branch. Plant B and good, that's the third branch. And plant B and defective, that's the fourth branch. Again, if you sum up the rows across, okay, we have 0.75%, 0.75 or 75% of the transistors come from plant A, and sum this second row across, 25% of the transistors come from B. And like we found above, if we sum the columns, okay, these two branches are going to give us all of the good transistors, 91.25%. These two branches are going to give us all of the defective transistors, 8.75%. If you add either the total row or the total column, you'll get 1, and that tells you we've covered all of the possibilities. Suppose instead we want to know that if the transistor, we want to know whether a transistor is from plant A given that it's defective. This is different from saying it the other way around, okay? Saying that is a transistor defective given that it's from plant A. This is the reverse, okay? So this is saying, is it from plant A given that it's defective? Maybe there's no way to trace the defects back to a given plant. So we want to make sure that we can answer this question. Say one of our customers calls us and has the bad transistor in his or her hand, okay? And basically as A's operations manager, you want to know where it came from. You want to know if it came from our plant. So here's Bayes' theorem, okay? This is the probability that a given transistor is from A, given that it's defective, okay? So how do we do that? We're going to find the product of all branch probabilities that lead us to plant A and defective. That's the first branch in our tree. And the denominator is the sum of all the ways we could get a defective transistor. That's going to include our first branch, but it's also going to include the branch that goes through plant B and leads to a defective transistor. Here's another way of looking at Bayes' theorem. Okay, so we want to find the probability of A and D on top, and then all the different ways to get to D. Okay, so let's go back up to our tree here. Okay, so we want to find A and D. Okay, and we can see that's this branch that goes through A and then defective. So here's the 0.075 or 7.5%. And then we need to find all the different ways that things are defective. Okay, so the way we're going to do that is we're going to add all of the branches that go through defective. That's this branch that goes through A and the second branch that goes through B. Okay, so again, we already did that here, and we got 0.0875 or 8.75%. So we're going to divide that numerator by that denominator, okay? And we have an 85% chance that if we are looking at a defective transistor, it came from plant A. And you might wonder, well, that's not terribly intuitive because 90% of what comes out of plant A is good. Yes, but plant A produces 75% of your transistors, which is the reason it's likely to have come from plant A. Okay, let's say instead we want to know What's the probability that a given transistor is from plant B, given that it's defective? Okay, we'd expect this to be a lot smaller of a number because plant B doesn't produce as many transistors. So we're going to go through the branch that gets us to B and defective, going back to the tree. That's this one, down through B and defective, 0.0125%. And our denominator is the same. It's all the ways to get to a defective transistor, 0.0875. You can see this is a much smaller number. Okay, it's only 14% likely. Okay, so again, it's much more likely if we're holding a bad transistor, it came from plant A, and that's because plant A made most of the transistors. Let's take a look at a medical example, which is really very relevant to all of us. Let's say we have a person with a certain set of symptoms, and the probability that a person who presents with these symptoms has hepatitis is about 80%. The blood test that's used to confirm the diagnosis of hepatitis will give us a positive result for 90% of the people with the disease. This is called a true positive. In other words, you have hepatitis and you test positive. It gives a positive result for 5% of the people without the disease. This is called a false positive. And while it's unnerving as a patient to get a false positive result, it's not dangerous. Okay? So again, what's more dangerous is a false negative, namely that the test does not pick up the disease when you really have it. Let's take a look at a table that we can build from this information. Okay, we know that 80% of the people, okay, who have these set of symptoms have hepatitis. That means 20% of the people who don't have those symptoms, don't have hepatitis. Okay, so this is the information we're given from the problem. The rest of the information has to be computed, and I'm going to show you these down at the bottom here. Okay, the probability that you have hepatitis and test positive, 72% here, is a conditional probability of 80% chance that if you present with those symptoms you have hepatitis, and a 90% chance that if you have hepatitis you'll test positive. Okay, this is a conditional probability of testing positive given that you have hepatitis. Multiplying those two together gives you 0.72. Okay. Down here we have a person who doesn't have hepatitis, okay, but tests positive anyway. That's the 20% of the population without hepatitis even though they have these symptoms, and the 5% of the false positive rate. Multiplying those two together, we get 0.01. Okay, adding these two, okay, the probability of testing positive is 73%. In this column, okay, we have the probability of having hepatitis and not testing positive. This is that dangerous case of a false negative. Okay, so this is the person who presents with the symptoms, has hepatitis, but the test doesn't pick it up. They test negative. Okay, so we said 10% of the people with the disease, okay, are not going to test positive. That was given. And then over here, we have the people who don't have hepatitis and don't test positive, okay? These are true negatives, okay? We're going to multiply 0.2, 20% of the population who has, does not have hepatitis even though they have these symptoms, with a 95% chance that the test is going to truly reflect that, okay? That gives us 0.19, okay? Again, you add these up, you get a 27% chance of testing negative, okay? So again, let's go back up to our problem statement. Okay, so again, here's The people who actually have hepatitis with these set of symptoms, 80%, the test will give positive results correctly for 90% of the people and testing positive. And that means you're going to get a false positive some of the time, okay? 5% of the time, okay? So again, this is where we're getting these other numbers from, okay? The 95% and the 5% here, okay? So these are 5% of the population who don't have hepatitis but test positive anyway. And over here, you've got people who have hepatitis but don't test positive, okay? So it's important to be able to look at the wording in the problem and understand what you're trying to solve here, okay? So let's go back down to our Bayes theorem and see if we can figure out what is the possibility that I have hepatitis given that I've tested positive, okay? So have hepatitis given that I've tested positive from our table is 72%. And if you look at the total column down here, there's a 73% chance of testing positive in any way, okay? So that is 0.72 divided by 0.73. This test is pretty sensitive, so given it's telling me I have a 98% chance of having hepatitis given that I've tested positive. And again, sensitivity of a test is the probability of it giving a positive result when the person actually has the disease, a true positive. And the specificity of a medical test is the probability of it giving a negative result when the person does not have the disease, a true negative. It's important if you're undergoing any medical tests to ask your doctor or your medical professional about these numbers, since as you can see, it does affect the result of whether or not you're actually ill, given that the test says you have a disease.